Biology students. Hello, hello. All right, so here we go. We're still in chapter 17, the ectothermic vertebrates. Again, those are the cold blooded vertebrates, so they are not able to regulate their body temperature. And in particular, now we're in 17, part B, the fish. And here we go. So, first of all, we look at the main group in this is classed osteichthyes. Again, the oste basically means bone, and the ichthys, Greek for fish, so these are the bony fish. And, I guess I should say, let's see, those of you who are doing lunch table chores, you are excused for being late, so that is just fine. Okay, so some key characteristics of the bony fish. First of all, there's just so many different sizes, shapes, colors, and behaviors. They're just such variety. I mean, really, I feel like it's that with almost any category of animals that you look at, just how much variety there is crazy. But we definitely see that here, and we're still just scratching the surface, and in many ways, quite literally scratching the surface of what there is to explore with fish because of how deep the ocean is, and it's something in the range of 1 or 2% of the ocean that we've really decently surveyed as far as discovering what's there. So I thought I would play a few little videos that demonstrate some of the different aspects of the variety that we see in fish. So first of all, we have this one that does this. All right. Not much I'm going to say about that other than there are some fish that have instincts built into them to make designs on the ocean floor like that. I mean, a circle within a circle and the ridges within the circle. And you saw there at the end how the fish was grabbing something that had kind of a little bit more color to it or like a brighter, shinier, or at least more white reflective object that it was going to insert. Okay. Next, we have this. So those are salmon that are jumping upstream, and some of you might know this, some of you might not. But salmon, they prefer to go back to where they were hatched as their mating place. And sometimes where they hatched is like miles and miles and miles upstream, and even up little waterfalls like that. And they swim upstream, and they swim up waterfall. Sometimes they swim up like drainage pipes and all that kind of stuff in order to get back to whatever pond or lake or stream is where they were fertilized as an egg and then where they hatched. Some dams have interrupted some of that, but then the fish find a different place to do it. Let's see. Let's see. A different place to go back to and to reproduce and hatch. They're they're young. I don't know why I was tripping on those words all of a sudden. There was something else I was gonna say about that, about the salmon, about the going upstream. Oh, how do they know that it mainly appears to be by their sense of smell slash kind of taste, but fish have a very keen sense of smell for being able to sense minute amounts of substances. And I have a slide about this later, but minute amounts of substances in the water, and that they like are born with a remembrance of what the almost like exact mineral content of the water was where they were born, and they're from the ocean. They're able to pick like which stream to go up, and then from there which branch of the stream, then which branch, in order to get back to where they were born from, where they hatched. But then that also kind of relates to taste buds. And here I'm going to give you the answer, the question and answer to number 2 of your video questions. Number 2 is approximately how many taste buds do catfish have? Approximately how many taste buds do catfish have? And the answer is 27,000. 27,000. Contrast that to humans. Average human has about 9,000 taste buds. So we're talking about a lot of fish have around 3 times the number of taste buds as a human. And I've also read that, I haven't looked into this more, but I've read that a lot of fish have taste buds basically all over their body. They're not just constrained to just their tongue and inside of their mouth like it is for humans. Okay, here's what we have next. Sorry about that. For some reason, when I click the button, it wants to start the video again. And okay, just another variety in shape and behavior. In this case, the pufferfish.
Sometimes a defeat can really be a victory. Let's begin with this pufferfish, minding its own business in this calm river delta in Tanzania, Africa. Enter the predator. In this case, a river otter cousin to the Yellowstone sliders. It's trying to make an afternoon snack.
Oops, sorry about that. I didn't think what I was doing off screen was going to stop the video, so let me start that.
Out of the pufferfish. How tough could it be? The otter captures the puffer. Well, sort of. I mean, not exactly. Okay, the truth is the puffer gulps water until it resembles a beach ball, and in the process transforms from a tasty morsel into a major pain. No matter what the otter tries, the puffer refuses to deflate himself. Naturally, the otter appears baffled. He set out to get a fish dinner, and instead he seems to be playing a ball game. The irony here is that the puffer is protecting both of them. The puffer has a poisonous gallbladder. If the otter actually ate the puffer, they both die. Puff Daddy survives, and the otter goes in search of another meal it can sink its teeth into.
All right, I mentioned earlier the depth and how we've just barely explored a lot of it. This one kind of, yeah, goes into a little bit of just hopefully giving some perspective of what the depth of the ocean is in a lot of places. Yes, it is. Oop. Okay. And then a little bit more, depending on where you look in the depth, oftentimes when you get to the deeper stuff, there are some pretty interesting things. Not all of these are deep sea fish, but quite a few of them are. So here is the Asian sheepshead wrasse. Then you have the very aptly named blobfish. Yeah, color-wise, a lot of the fish, when you get deep down, because you probably noticed in that previous video, it's around 1,000 meters deep. or 1 kilometer deep, which is only like 6/10ths of a mile, that you don't really get any sunlight penetrating that deep. And so once you're beyond that, you get a lot of fish that are basically colorless, but sometimes they still have some color, and sometimes they have like reddish colors going on. And then you also have quite a few bioluminescent fish that are able to create their own little amounts of light, almost like little night lights that they create. Sometimes they're for defensive purposes, sometimes for predatory purposes of being able to lure and then eat their prey. All right, anyway, so blobfish, the common fangtooth. Yeah, I would not want one of those swimming around near me. The frogfish, the young boxfish. It was kind of cute, isn't it? Yeah, and the sarcastic fringe head. So check it out. It looks usually like the picture on the left. Kind of somewhat ordinary fish looking, though a little strange. But then if it's threatened, or usually it's that, like if either for trying to intimidate one of its own kind of fish or defend itself from against prey, it can open up its mouth really wide. And the right hand picture is what it looks like when it opens up its mouth. You can see like the multiple rows of teeth. You can see, I think, a little bit of its tongue. There's some. Oh yeah, most fish, their jaws are not attached to the rest of their skull, and so they can do like stuff like open up their mouth and then actually like protrude their mouth out a little ways from the rest of their head as a way of making it easier for them to catch their prey. Stuff like that. All right. So next bullet point: different from most vertebrates. How are fish different from most other vertebrates? Well, a few things. First of all, they usually have a flat spindle-shaped body. A flat, flat, whether it be side to side flat or top to bottom flat. And then spindle shaped. What we mean by that is spindle shaped is this: if you took like a rectangle and you pinched the two ends to make it rounded, so it kind of comes to a rounded point at the front and a rounded point at the back. I don't know if that was a good way of explaining what I mean by spindle shaped. And then they're also different in that the ribs, pectoral girdle, and pelvic girdle. So we talked about those terms in the 17A video, but those are usually cartilaginous. So it's cartilage rather than bone. So again, think of like the bridge of your nose is cartilage. It can be pretty hard, but it's not technically bone. And then also, fish are different from most other vertebrates in having fins. So speaking of fins, I have a image here that shows some of the different fin names. So if I start at the front, looks like the first fin that we get to are the pectoral fins. Think of like you probably know the term your pecs, you know, like you would do push-ups to work out your pectoral muscles. That similar term here, we have pectoral fins, and then on the bottom there are the pelvic fins. Um, Anal fin, some fish have. All of these, some fish have, some don't. It just depends. But then at the top, you have the different dorsal fins. So dorsal of or pertaining to the back. So this image shows an example of a spiny dorsal fin that some fish might have versus a soft dorsal fin that some fish might have. And then sometimes you have stuff like an anterior dorsal fin, so a dorsal fin that is closer toward the head, or a posterior dorsal fin, one that is closer to the tail. And then the main tail fin of a fish is called the caudal fin. You might recall caudal of or pertaining to the tail as opposed to cephalic of or pertaining to the head. So the caudal fin is the tail fin. And that's one of the ways that you can tell the difference between something that is a fish versus something that's like a whale or a dolphin that are mammals is in fish, the tail fin it's aligned, it's oriented up and down versus whales and dolphins, things like that, porpoises, their tail fins, their caudal fins are oriented horizontally. Anyway, just a little tidbit there. Let's see, scales. You kind of pictures that. And I guess, yeah, let's do number 5 of your video questions. Number 5 is most brands of what type of product often use fish scales as an ingredient? Most brands of what type of product often use fish scales as an ingredient? And the answer is lipstick. There's just something about the texture and the sheen that fish scales have that a lot of different lipsticks use fish scales as an ingredient. So, yeah, hopefully I didn't just ruin wearing lipstick for some of you. Okay, so that was number 5. All right, moving on. So we talked about fins. All right, air bladder. Air bladder is a thin-walled sac in the body cavity that enables the fish to control its depth and to maintain its depth without swimming. Gases diffuse into and out of the air bladder through the bloodstream or by contact with the digestive system. So basically, if a fish wants to sink down lower, in order to go lower, the fish needs to be more dense. The way that the fish makes itself more dense is it removes the air from its air bladder and it makes the fish denser, and the fish will naturally sink to a deeper depth. But then if the fish wants to rise higher in the air, it should be less dense. And how does it do that? It takes oxygen, or just in general gases, from its bloodstream, because I think it might be oxygen and carbon dioxide, from its bloodstream, and it transports those gases into its air bladder to slightly puff up its air bladder like a balloon, and it makes the fish less dense, and so it naturally rises higher. And by subtly changing how much air is in its air bladder, the fish is able to control at exactly what depth the fish will just naturally float without having to exert any effort. So if the fish is like, I want to be a little bit higher in the water without having to exert any effort to actively swim at that height, so it's just like us. In order to go deeper underwater, in like a swimming pool, you have to exert effort in order to keep swimming in order to stay at that depth. Fish can just alter how much air is in their air bladder in order to change what depth they're at without having to exert any additional effort. Okay, so that's that. Let's move on. So that's different from most vertebrates. So then body covering. And we mentioned scales already. Scales, one of the things it does, gives a certain amount of structure and protection to the outside of the fish. But then outside the scales, most fish secrete a type of mucus that covers their body. And different studies have shown that the mucus can reduce water friction by about 66%. So it makes it so that the fish are able to glide through the water way, way, way better. And the Olympics, I recall briefly, I think it was the Australian Olympics, briefly allowed full body swimsuits for the swimmers participating in the Olympics. But then they found that just like record after record was getting shattered because the amount of resistance, or the drag force of the body moving through the water was way lower because of the swimsuits. And in particular, some of the swimsuits were designed after the design of shark scales, and the way that shark scales are designed as far as their shape and the way that they're layered, stuff like that. So I think that one Olympics is it that they use for full body suits like that, and then since then they have altered it to say like what the maximum amount of your body is that you can have covered with a swimsuit in order to be able to compete. And so like for the guys, it's just like from their waist down to about their knee, I think is all that they can have covered, kind of a thing. So speaking of swimming fast and swimmers, let's do number 1 of your lecture questions. Number 1 is, how fast can tuna fish swim? How fast can tuna fish swim? The answer is 43 miles per hour. 43 miles per hour. That's number 1. And 43 miles per hour might not sound that fast, because we're used to driving like 65, 70. But to put this into perspective, the fastest that Michael Phelps was able to swim at his peak, the fastest that he could swim was 6 miles per hour. And so, yeah, tuna fish, we're talking 43 miles per hour. So that's what, like 7 times as fast as Michael Phelps. which 6 miles per hour might be like, that seems so slow. But if you think about swimming a distance of 6 miles in 1 hour, that is super impressive. I'm not saying that Michael Phelps could swim 6 miles in 1 hour. I'm just saying that was his peak speed. Yeah. Anyway, so mucus helps fish be able to swim a lot quicker. And then chromatophores. Chromatophores, these are branched cells responsible for producing some of the pigments that color fish. And fish can be super brightly colored in all sorts of different patterns, but some fish can control which pigments are produced when in their chromatophores in order to camouflage themselves. So here's a video that shows that with a flounder, if I recall correctly. All right, here we go. All right, somewhere on the drum, there is a fish. You might have picked up at this point that it's toward the right-hand side, like the right-hand side of that rope or chain, whatever it is, around the middle of the drum. And in just a second, you'll see it move a little bit better. You can kind of see its eyes toward the left-hand side. There it is moving. But like from a distance, especially at a casual glance, would not be able to see that thing at all. It was so well blended in. Kind of like what we saw with the octopi. And in just a second, it's going to swim off and it's going to find a new place to land. See, its color is quite a bit different. And check out where it lands and how it just blends in again. So this would be a fish that is flat from top to bottom, kind of like stingrays, manta rays. Those are a couple of the other things that I can think of that are similar. And just like that, it found a new place. And its eyes you can kind of make out pretty easily just because you knew that they were eyes, but notice all the other little dark spots around it. If you didn't know that those eyes were its eyes, you would not easily see. And then even added some other dark spots for it to fit in better. It's like, leave me alone, bro. Just trying to live my life. Okay, moving on. All right, so that was chromatophores. Next bullet point, counter shading. So counter shading is where the fish has a darker upper half and a lighter lower half. And what it does, it allows fish to better protect themselves from other fish who would want to hunt them because of making it harder for them to be seen. But then it also makes fish that are wanting to do the hunting easier for them to do the hunting because, again, it's harder for them to be seen. So what we have a dark upper half that makes the fish viewable from above blend in with the dark depth. So like if you're in water looking down, it's darker below because less light is getting down there. And so the upper half of the fish is dark. So if you're above the fish looking down, the dark upper half helps it blend in with the dark depth. Then if you're underneath the fish, below the fish looking up, you're looking up toward the surface where there's more light. And so it's lighter when you look up, and the bottom half of the fish is lighter to blend in with the lighter surface. That's what's going on with counter shading. Okay, next. This is just a picture showing some of the counter shading. So notice how much lighter the bottom half is than the top half. Yep, counter shading. And then digestion in fish. Not much that I really have here. Well, other than this little video that we'll watch in just a second, showing one of the ways that fish eat, as far as like how they get their whatever they're trying to eat into their body. But like, I mean, animals just about, well, yeah, fairly elaborate digestive system. I mean, we might see a little fish and be like, oh, it's just a little fish, but has intestines, has like a liver that helps produce some of the digestive enzymes, has a gallbladder. You heard that in the pufferfish video of a gallbladder that's poisonous to some of the animals that would want to eat it. So stuff like that. Okay. But I found this pretty interesting. This is another one of those smarter everyday videos about how fish are able to get the food inside of their bodies sometimes.
Hey, it's me, Destin. Welcome back to Smarter Every Day. So as dads, when you go fishing, you spend a lot of time thinking about how to get the fish to bite, but you don't really think about how mechanically the fish do the bite. Does that make any sense? So today on Smarter Every Day, we're going to go to James Cook University in Australia and look at how a fish bite takes place in slow motion using a Phantom camera. You're getting smarter every day. Okay, so how do fish eat? So they suck food in, but they have to generate that flow, right?
Are you talking to me?
Yes,
Sorry.
I am, Dr.
I'm
Seymour.
trying to do two things at once here.
All right, so we've got a big tank of barramundi. Am I saying that right, Richard? Mm-hmm. Why do you have a stick and a string here?
Okay, this is the stick of death. This is what we use to feed everything with.
Right.
So if we hold that over the tank on the water, then you'll be able to focus on that, and you'll be able to see the barramundi come up and...
Okay, got it.
Alright. Here he comes. Gone.
Actually create that flow inwards? Are they like increasing the chest cavity somehow?
It's the buccal cavity of the mouth.
So what?
The buccal cavity of the mouth. So they'll open their operculum, which are the gill flaps, and they open their mouth wide, and that sucks the water in. So they're basically producing a vacuum behind them.
Buccal cavity.
Yep.
When they open their mouth, why does flow not come in the gills?
Because they open the front first. So you'll have a look, and you see it on high speed. They'll open here,
Yeah.
and then that'll go. And they'll push all the water, then comes back out through the back of the gills. When you see it on the high speed,
So that's
it will
how
make
they.
sense.
No way.
Yeah.
Okay, I just had that moment where I figured it out. So
Ta-da!
yeah, make sure I did this right. So the fish opens his mouth.
Yep.
And he starts flow in.
Yes.
So you have fluid momentum going in, and then he still has momentum going in. And if he doesn't get rid of that somehow, it'll push him backwards.
Yep.
So when it goes in, after he gets it in his mouth, then he opens his gills and he releases that momentum.
Yes.
Shut up!
Yeah,
I've been
and-
fishing my whole life and I didn't know that.
And you'll see it on the high speed.
Really?
Yeah.
All right. Dude, that's awesome.
Do it out here in the light.
Whoa!
So the fish is coming up to the food, and instead of accelerating the whole body to grab the food, fish have a very complex mouth where they can throw the jaws forward. So instead of throwing the whole body mass forward, at the last moment you have this very complex mouth with all these bones that just opens up. So it closes that gap with the prey a lot quicker and a lot easier.
Okay, so he doesn't have to accelerate the mass of his whole body, just the front jaws.
the jaws. And so when the jaws are thrown forward, as Jamie explained, it's creating this huge volume, and the water has to rush into it, and then out through the gills. And so you get this suctional feeding.
That's awesome.
So yeah, so it's suction feeders, ram feeders, you can call them.
That was awesome, really.
Yeah,
Do all
that's
fish do this?
No. No, only a few fish actually suck their prey in, because these guys don't have teeth as such,
Okay. So teach me the terminology. So there's the buccal cavity.
which is the mouth. Yep.
They open the buccal cavity, and then they open the gills.
The gills, or it's the opercular flap. So the gills are behind this flap. So when that's closed off, the only entrance is in through the mouth. Water sucks in, then you've got to get rid of it somewhere. So you then open that out and it'll all flow to the back end.
Because you have to dissipate momentum.
Yeah.
Okay, James Cook University just taught me something about how fish eat, and I'm assuming you. Does this work on like your goldfish in your aquarium?
Yeah, same sort of thing.
When you put the flakes in, you're gonna see him open his mouth and then open the operculum and dissipate that over the pectoral fin. Yeah, you're getting smarter every day. I'm Destin. Have a good one. Have you caught anything yet?
No, sir.
Do you enjoy it anyway?
Yes, sir.
Do you wish we had an audiobook to listen to?
Yes, sir.
Which one?
Captain Neil.
Pull, 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 son, pull it.
I got a fish.
There you go.
Keep reeling it in.
All right. Okay.
Still has a worm in his mouth.
He does. Let's let him eat that worm. So this is what happens. He opens his mouth right here. The water gets pulled into his mouth, and then he opens his gills after that, and he shoots the water out of that. Does that make sense?
Yes, sir.
Hold on tight. Don't be scared. You ready? Now slowly let him back in the water. There you go. All right, so that's how fish eat. If you are interested in supporting more fishing trips and more episodes of Smarter Every Day, you can support us by going to audible.com/smarter and getting a free audiobook. Does that sound good to you?
Yes, sir.
What audiobook do you recommend?
20,000 Leagues Under the Sea.
That's right. Where do we listen to that?
In the car.
That's right. So if you're interested in helping Smarter Every Day, go to audible.com/smarter, download a free audiobook. You can get 20,000 Leagues Under the Sea, and you can help Smarter Every Day. It'd be a real good thing. Anyway, thank you very much. You want to say thank you?
Thank you.
Anyway, I'm Destin.
Bye.
And bye. I'm Destin. You're getting smarter every day. Have a good one.
So there you go. Just a fascinating and amazing design that you have going on there. So that kind of moves us on to respiration, where there's a similar thing that happens with fish. So the term you might have heard in that video, either the operculum or the opercular flap. The operculum is what commonly some people refer to as the gills, but it's the flap that covers where the gills are that the fish can open and close. And then behind that operculum on the side of its head are the gills. And so what happens is the fish sucks water into its mouth and then expels it out as gill slits, or expels it through the the operculum is technically the flap that covers the gill slit. So the fish sucks water in its mouth and then expels it out as gill slits. And what that does is it flows the water across the gills. And then oxygen molecules that are dissolved in the water. So we're not talking about the oxygen atoms that are part of the water molecule. We're talking about O2 molecules. So two oxygen atoms bonded to each other. That is just it makes up, I don't know, a couple percent of the air that we breathe. Those oxygen molecules dissolve into the water. And so what happens is as the water flows across the gills, those oxygen molecules diffuse into the blood vessels in the gills. And then meanwhile, carbon dioxide molecules, so, respiration, we are same thing as our bodies. We take in oxygen. That oxygen gets used for part of the process for making ATP. And then the result of that is where we end up with a bunch of carbon dioxide, and we need to get rid of the carbon dioxide. So meanwhile, carbon dioxide molecules diffuse out of the blood vessels and out into the water. So that's the gist of what's going on with fish respiration. So fish, when you take them out of water, they die because their gills are designed to get oxygen that is dissolved in water. It's not designed to get oxygen molecules out of the air. And so they actually die of suffocation when you pull them up out of the water because they can't get the oxygen that their bodies need in order for their, ATP processes, their ATP manufacturing processes to continue, and then cells start to die. And you get organ failure and stuff like that. So same thing as if a person died of like strangulation. It's the same overall method of death, the lack of oxygen. Except one main type of fish, there's the lungfish, and the lungfish can breathe via lungs, and the lungfish can, I think it's something like can live out of water for a few months. if I recall correctly. I do think it's a few months that they can be in a completely dry environment and they're able to get they're able to get oxygen out of the air, unlike most fish, because they have a type of lung that enables them to do that, but only works. It can only support them for so long. Okay, moving on. Circulatory and nervous systems. So, the term olfactory sacs, what happens is fish can smell incredibly minute amounts of substances dissolved in water. And then there's also something called the lateral line. And the lateral line is kind of like a sense of hearing. It allows the fish to sense pressure changes, to sense vibrations, stuff like that in the water. And yeah, fish also, we don't think of fish as making sounds, but there are fish can do some kind of a certain amount, I'm sure it depends on the species, of communicating with each other by different types of cracks and pops and rates at which they might shake their body and different things like that that allows other fish around them to pick up that info on their lateral line. But then I've also heard it said that fish do not like rain very much. Like if you're talking like a fish is in some kind of a pond, they do not care for it very much when it's raining because the water falling onto the surface of the pond creates just like a thunderous amount of sound that their lateral line is picking up because of all the vibrations all over the place on the surface of the water. And I've heard it compared to if like you were in a metal shed with like a flat metal roof and it was raining really hard. You just had that really, really loud sound of all of the big raindrops pounding onto the metal roof of the shed. I've heard it said that's kind of like what an average fish would hear when it's raining in the body of water that they're in. Okay, and then reproduction. So the two main terms with fish reproduction is spawning and milting. So spawning is releasing or the laying of eggs in the water. So the female spawns and then the male milts, which milting is releasing milt, and milt is the milky fluid containing the sperm near the eggs. Yeah, so the female releases eggs, the male comes along and milts, and then external fertilization happens, and then those eggs grow and develop, and you have new fish. Okay. Let's do, this is somewhat random of a time for this, but let's do number 4 of your video questions. Number 4. Electric eels and electric rays, so we'll talk about rays just really briefly later, but electric eels and electric rays produce enough electricity to kill what type of animal? And the answer is a horse. Yeah, the amount of electricity that electric eels and electric rays can make would be enough electricity that if applied the right way, it could kill a horse. And that's one thing to consider with things like in the Bible, the references to fire breathing, fire producing animal is we do see in nature animals that can use chemical reactions to create light. Other animals that can use chemical reactions to create electricity, static electricity. Other animals that can create or that can use chemical reactions to create explosive, well, like the bombardier beetle is one that has like a chamber of one kind of chemical and a chamber of another kind of chemical, and when it combines the two, there's a small explosion, that tremendous amount of heat and force that it is able to aim at something that is wanting to incapacitate or kill. That when you combine different things like that, it's like it's not too far-fetched to imagine an animal that is able to, or that was able to create the right chemical reaction to have a combustible gas, and then another chemical reaction to create an electric spark in order to create a flame from that combustible gas. So that could have been what was going on there. All right. Okay, nothing else to talk about that slide. Next slide. Next we have, so all of that was stuff about class Osteichthyes, the bony fish. Now we have class Agnatha, the jawless fish. So fish without jaws. And the two main examples we have here are hagfish and lampreys. This picture here is a picture of a hagfish. Nice and cute, huh? And then some lampreys. So you can see the mouth with the teeth around it, and there's no jaw. Okay. And one of the main things to note about hagfish is they have a really unique defensive mechanism where they create this like sticky slime, basically. And I have a video that shows some of that.
The first time I saw a hagfish was while I was volunteering here at Scripps back in high school. My predecessor, Ron McConaughey, was an old hand at collecting animals. He was a great collector. So one day, Ron asked me to go out and help him collect some of these animals out in the La Jolla Canyon offshore. We went out. I had no idea what to expect other than he handed me a line and said, pull. 1,000 feet later, up came this small minnow trap that was filled with these wildly squiggling animals and leaching with this very strange mucus snot type mixture.
It's at La Jolla. It's down by San Diego. Looks like La Jolla, but La Jolla.
Okay, let's see. Now, because I knew you guys were coming today, we set up a small aquarium to show what the hagfish look like, maybe out in the deep sea. We collected these animals from about 1.5 miles from where we're standing right now, out in about 1,000 feet in the submarine canyons just offshore here in La Jolla. So in the world, there's about 64 species that have been described throughout all oceans and basically most of the deep sea environment. This species is Eptatretus stouti, and it's known as the Pacific hagfish. It has this nice dark pink on the top with a light bottom underneath. They don't have true eyes. Instead, they have this small eye spot that you can see right here. It's not a complex eye by any means. They're actually virtually blind, but they rely on other senses, like their sense of smell, which is highly acute, and their sense of touch. The animal has probably adapted this very smooth body so that it can move around very easily when it's inside of a dead whale or a dolphin. Okay, so the way you see these animals coiled up like this is probably the way they spend a lot of their time down on the deep sea. Now, hagfish don't have true jaws like most fishes out in the water. What they do is they have this rasping-like tongue. They'll swim over to whatever they want to feed on, latch into it, and they're able to tie their bodies into a knot and move that knot up and down their bodies. So what they'll do, they'll grab onto that whale, make a knot, push that knot down its body until the knot is pressed up against the whale, and then they're able to pull their head out with that mouthful of flesh, and that's the way they eat. They'll do that a few times until they're able to make a big enough hole to where they can then even actually go inside this animal and eat it from the inside out. It's just amazing what these can do. But the most unique thing is this sliming capability that they have. Just one of these can turn an aquarium like this into solid slime in about 3 seconds. They use this as a defense mechanism to escape from predators and anything else that they want to completely repulse, including myself when I first saw these animals. Because hagfish are such good slimers, we found this to be a pretty good way to transfer animals from one container to another. This is what happens. And so this is just a little bit compared to what one animal can make out in the wild. And as you can see, it's a very unique type of structure. And it's not the most appetizing thing in the world. Matter of fact, this is enough to suffocate some fish. And as you can see, it's just really thick, amazing type stuff. Now, you might wonder, what is this stuff? Well, it's a protein, and the molecules are stored in those little slime glands that we saw earlier along the sides of the body. When the animal puts this protein into the water, the protein explodes. So this slime is probably the reason why these animals have survived for 300 million years, is that it's an amazing defense mechanism. I'm disgusted, and I can only imagine what a predator might feel if it should end up with a mouthful of this stuff. I'm fortunate enough to have interns here work with me over the summer. Her name's Lily Bullock, and this is the first time Lily has ever seen slime like this before. And if you want, okay, good, you're bold enough to hold on to the stuff. What's it feel like?
It's not. It's kind of sheer. Mucus, I guess. Kind of, I don't know, kind of rubbery, actually. And very slippery. And disgusting.
Pretty weird stuff. Great to use for Halloween, huh?
Definitely.
Yeah, disgusting was the word that was coming to my mind too. All right, just about wrapping it up. So that was class Agnatha, and then finally class Chondrichthyes, and this is the cartilaginous fish. So this is what has sharks, rays, and skates in it. And the main thing is rather than producing bones, they produce cartilage. Yeah, so their skeleton is made of cartilage instead of bones. And but another difference is rather than one opening where the operculum covers where the gills are, most sharks have 5 to 7 gill slits per side. And they do not have an operculum that covers it, so they just have these slits that can kind of open and close. And then they don't have an air bladder. Instead of an air bladder, they have a large liver. Like the liver might be like, I think it's something like 25% of their volume. And it's very oily, and oil floats. And so that gives them a lot of their buoyancy, but it makes it so that sharks, rather than being able to just modify how much air is in their air bladder in order to adjust what depth they're at, sharks have to actively swim to maintain whatever depth they're wanting to. So that's that. And speaking of sharks, let's look at video question number 3. This is our last one. And it says, how many teeth will many sharks have throughout their lifetime? So what happens is sharks, they have an outer row of teeth, and that's their main row of teeth, but then they have multiple inner rows of teeth that are constantly growing. And so when an outer row of teeth falls off or breaks off or gets ripped off as the shark is attacking its prey, then a tooth from the next row in is gradually making its way out to replace it. And so sharks are constantly growing new teeth that are new rows of teeth that are working their way outward to become the primary row of teeth. And the answer here is 20,000. How many teeth will many sharks have throughout their lifetime? Number 3, answer is 20,000. And then rays and skates, these are flat and thin with a ventral mouth, so a mouth on their lower side. And I have a little video of some small little rays here. Cute little things. Here we go. The music is kind of cheesy, but just wait until it comes up to where it's on the glass of the aquarium. It's pretty funny looking. Okay. That wraps it up for fish. I know this one went a little bit longer, but I usually figure one of these videos is probably 2 days worth of class. So it's like an average of half hour per class period, basically. And I think the next one will be a little bit shorter, the amphibians. The fish, there's just quite a bit to talk about and to look at. But hopefully that helped with your homework. And hopefully you also got all of the video questions done. And yeah, hopefully find it interesting. I think fish are quite fascinating. I mean, really just like all the animals, but just some really cool behaviors and structures and everything like that going on. All right, that will wrap it up, and have a good one.